Welcome to this video where we continue to talk about content contained in the book Introduction to Nonlinear Control. And in particular, in this video, I'm going to talk about observer design for linear systems. So continuing with chapter 16. This chapter here starts a new section. Namely, we are going away from just the analysis of dynamical systems and away from controller designs now to observer designs, where we start with the simplest setting, namely the setting of linear systems. And to put that into context, the results so far mainly relied on the assumption that we had access to the full state X. Meaning, when we were designing a controller, we assumed that we know the state X, and that allowed us to define a feedback controller U is equal to Kx, a function of X. However, normally not the full state is known, and only a subset of the states in terms of an output y and rp, where p is the dimension of the output, x is usually in Rn, and p is smaller than n. If we only have measurements y available but not the full state x, well, that means that we cannot design our controller based on x, and we can only define it as an output feedback controller, meaning we can only use the information contained in y to define the controller, or we need to define an observer. That's what we are going to do now, to reconstruct x, namely to get an estimate denoted by x hat of the full state x, to ensure that x hat is converging to x asymptotically, exponentially in finite time to the true state x, and based on that information then to define a feedback controller based on x hat instead of x, and then to analyze the properties of this overall closed loop system. To make a very simple example and to get started, the setting we're going to look at is the setting visualized over here, where we have a plant with a given input, given output, with internal state x. And we assume here that our input is defined as a linear feedback, u is equal to kx hat, where here we already indicate that we are using the information of x hat based on an observer with the initial internal state x hat instead of the true state x. And we start with the assumption that our observer as an only input has the input u. So the only information that is available to the observer is u. To fill that a bit with additional assumptions, we assume that our plant, so the plant here is given by a linear system of this form, x dot is equal to ax plus bu, the output y is cx plus du, and we assume that the output y is known, the input u is known, however the full state x is unknown, and also the initial condition is unknown. We start with the assumption that A is Hurwitz, meaning that the system without input, or more precisely, the origin as an equilibrium of the input of the system without input is asymptotically stable. So then, first question, under these assumptions, how would we define an observer that ensures that x hat converges to x? Well, we simply use a copy of the dynamical system, meaning we assume that we know the matrices A and B, and then we can define our observer dynamics through x hat dot is equal to ax hat plus bu. And using the notation already mentioned before, here we assume that x hat is an estimate of the state x, which means we can define the error between x and x hat simply through E is x minus x hat. Why is that helpful? Well, that's helpful because now we can look at the error dynamics, taking the derivative of E with respect to time, plug in the definition giving us x dot minus x hat dot. Then we can plug in the dynamics of the plant and the dynamics of the observer, and we can simplify corresponding terms. Namely, we can observe that the input doesn't play a role here, and we are left with the dynamics A is equal, E dot is equal to A times E, meaning we simply have the system E dot is equal to AE, which tells us now how to check convergence of the error variable, which under our assumption occurs here. Namely, we have assumed that A is a Hurwitz matrix. That implies that the error E of t is going to 0 for t going to infinity, which means that x hat is converging to x, meaning the estimated state x hat is converging to the true state x, which allows us to asymptotically recover the true state x. And that's the case for all inputs u, since these calculations told us that the input here cancels out. However, this is of course very restrictive because we relied on the assumption that the matrix A is Hurwitz, and we actually didn't make any use of the information that is available to us in terms of the output of our plant. But what we can do is, well, we can use that information here and also use the output y as an input to our observer. In particular, we introduced this additional term here, taking the mismatch between the actual output and the estimated output into account. And where we have now this degree of freedom in terms of the output injection term L. So same assumptions as before in terms of our system. Our plant is still driven by the linear dynamics here, defined through A, B, C, and D. We have a copy of these dynamics to define our observer, again defined through A, B, C, and D, but with this additional output injection term. How does this help us, this output injection term? Well, we can again look at the error dynamics. First define the error E is equal to x minus x hat, then consider the derivative, plug in the information we have in terms of the plant dynamics and the observer dynamics. We again see that the input cancels out and also the component with du cancels out. We can simplify the expression, and what we are left with is simply A plus LC times the error as the closed loop dynamics for the error dynamics E. As before, the error dynamics are independent of U, and now we are left with the system dynamics E dot is equal to A plus LC times E, where as a different to the situation before, we now have this additional term L times C with the degree of freedom in selecting the matrix L. And if we recall the properties of controller design for linear system using pole placement, well, then we see that here we actually have a similar structure Namely, if we want to guarantee asymptotic stability of the dynamics here, then we need to guarantee that A plus LC has all its eigenvalues in the left half plane. A plus LC has the same eigenvalues as this matrix here, where we have taken the transpose, and that is the same structure as A plus BK in the case of controller design, where we have designed the matrix K to ensure asymptotic stability. Here, instead of controllability, we need the concept of observability, depending on the matrix A and C. If the system is observable, which is defined and discussed in chapter 3 of the book, then L can be defined such that A plus LC is a Hurwitz matrix, or also under the weaker assumption that AC is detectable, then that also already implies that we can define a controller, an observer, such that A plus LC is Hurwitz, which means that the error x minus x hat converges to 0. So we can essentially use the same steps as in the controller design in terms of pole placement to ensure that in this linear system setting, x can be approximated through x hat. This answers the first question in terms of how to design L to recover the information of the state of a linear system. The second question that was stated at the beginning of these slides was, can we then also use the estimated state for controller design? So what we had so far was, well, we have our dynamics of the system, so the plant dynamics. We have our Lüneberger observer, where we have defined the matrix L in such a way now that A plus LC is Hurwitz. And now as a next step, we can design U is equal to Kx, so this degree of freedom here, to again guarantee certain properties of the overall closed loop system. Namely, if we plug that controller into our system dynamics, what we end up with is the expression here, visualized here, A plus BKX plus BKE. So here we have our error in terms of x minus x hat. And if we combine that with the error dynamics, so if we combine this expression here with the dynamics of the state, just depending on x and E, then we end up with the overall closed loop system dynamics represented here. Now, instead of a system of dimension n, we have a system of dimension 2 times n, where we can analyze the closed loop properties and convergence properties. And we see that asymptotic stability of the origin of this system depends on the eigenvalues of this block matrix and the eigenvalues of this block matrix here. And if the system is controllable and observable, then we can choose K and L in such a way that these block matrices are Hurwitz, which means we can guarantee that the error is going to 0, which then additionally implies that x is converging to 0, allowing us to use an output feedback controller, relying on an observer to control the state of a plant and ensuring that we get convergence to 0. The fact here that we can choose K and L independently in terms of asymptotic behavior is called separation principle. This is true if we are only interested in the asymptotic behavior. In the transient response, the selection of K influences the behavior, or their K and L are not independent, and they influence each other, or they influence the speed of convergence, or the transient behavior of the states X and the state E. This representation here in terms of X and E helps us to understand the closed loop properties in terms of stability of the origin. An alternative representation that is usually used in the implementation is, instead of augmenting the state X with the aerodynamics E, is to augment it with X head. That's equivalent, so we can get an equivalent representation used for implementation of such a output feedback controller relying on a Lüneberger observer. And also here we get that X hat converges to X, but the convergence is not as obvious from the matrix here. So this was one example of an observer design, and you should have understood now the concept of an observer, namely recovering the information contained in the state X just based on output measurements Y. And then in this case the Lüneberger observer is a simple observer for linear systems, which can be used similarly, or using similar concepts as a linear controller by designing an output injection term L instead of a controller matrix K. Other observers for linear systems here in particular would then be a minimum energy estimator, extending the idea of linear quadratic regulators, so optimal controller designs now leading to optimal observer designs. And here the setup we start with is again a linear system, but now we additionally assume that we have uncertainty and disturbances and noise present here through B bar times V and this additional noise term W. Then the idea of a minimum energy estimator is to try to find a system of the form here where we've simply replaced X with X bar, and the interpretation here would be for given inputs and output Y, so that's the same setting as before, we will try to find X bar which satisfies these dynamics here and at the same time minimizes the cost function here, which is a cost function depending on the initial condition here with respect to current time and with respect to disturbance sequence V. But other than that, so the objective function here is pretty similar to the case of the linear quadratic regulator, where we try to minimize now the effect of the disturbance and the effect of the noise over the horizon from -infinity to the current time t. Here Q and R are design parameters which need to be defined as positive definite matrices. even though it looks like J here is a function of the noise W, we can replace W here with the expression which only depends on Y, X bar and U, and replace that in the expression of the objective function. So it's really just a function of the disturbance and the current state. So the interpretation then is of this cost function is given here. Given U and Y, find the disturbance V with minimum energy and an estimated state that explains the observed inputs and outputs best under the assumption that our system evolves according to these linear dynamics. And as before, in terms of the linear quadratic regulator, Q and the solution will be optimal just with respect to the selected Q and R. And here, a large Q penalizes the noise W and to some extent then neglects the disturbances, whereas large R penalize the disturbance but then neglect the noise. So the choice here should depend on how much do we trust the actuators, how much do we trust the model versus how much do we trust the sensors that we have at hand. With these definitions, a corresponding result that can be shown is that if we have a system that is controllable and detectable, here controllable with respect to this matrix B bar, and if we look at the underlying optimization problem, so minimizing the cost function subject to the linear dynamics, then it can be shown that there exists a solution to the so-called dual algebraic Riccati equation stated over here, such that the matrix A minus LC is Hurwitz and L defined through the solution of the algebraic Riccati equation, giving us the minimum energy estimator of the form that we had before, meaning defined through this output injection term and a copy of the dynamics. The minimum energy estimator is one way to derive a dual result to the linear quadratic regulator. So dual result from between controller design and observer design. A different way to design an observer is going along the lines of the so-called Kalman filter, which has a different interpretation and different motivation, but leads to the same results. So here again, we look at a dynamical system or linear system of this form, but then assume that V and W represent functions of zero mean Gaussian white noise with corresponding covariance matrices. So here R-1, Q-1, using the notation from the minimum energy estimator. And here, since this is Gaussian white noise, represented through the expected value and delta defining the Dirac delta function. Then, under these assumptions, X hat, in this case, obtained through the minimum energy estimator, actually minimizes the expected value here. And if we start differently and start with the minimization problem here instead of the objective function minimizing the minimum energy, then that's the derivation corresponding to the Kalman filter, which then leads to the same result as the minimum energy estimator. Just as a final comment then here, so this was the presentation of observer designs in terms of Lüneburger observer and minimum energy estimator and Kalman filter in the continuous time setting. Similarly, this can be used in the discrete time setting, and similar results hold where we just have to tweak little things to make it work as well there. This concludes the content I want to cover with respect to chapter 16, and then the next video will show extensions to nonlinear observer designs covered in chapters 17 and 18.